Okay, hello everyone. And my name is Hao Dong, and I'm now a postdoc at LOM. And previously, I obtained a PhD degree in acoustic at Nanjing University, and I'm now working with Simon Felix and Jean-Baptiste Doc. And today, I want to introduce briefly my previous work in Nanjing University. These are actually two aspects and can be concluded as the electroacoustic structure optimization and design. And it contains two aspects. The first is horn shape optimization based on the multimodal method. And the other is a design principle for higher order bandpass subwoofers. Their connection is not very close, but they represent the previous topic I studied. So the contents include these two parts, and both with a short summary. So the first topic is the shape optimization using the discrete model, multimodal method. And first, I will give a brief introduction. The acoustic horn, as we know, has the advantage of high efficiency, and it can control the directivity of the radiated sound. And it has been widely used in conjunction with a loudspeaker driver to form a horn-loaded loudspeaker system. And it also has applications in musical instruments such as the brass instrument. And in terms of the horn loudspeaker, we have two main fields of applications. For the first application, we want the sound reproduction in some audio systems. For example, the audio hi-fi system or the professional audio line array systems. And in this case, we want high efficiency and matched impedance, as well as frequency independent or constant directivity over a desired response, desired frequency band. And another small area of application is the long-range communication use. This picture is a megaphone, and in this case, we want the sound can propagate to a very long distance. So the design goal is the high on-axis SPL. And we should design the horn shape to reach these goals. And classical horn design includes these two aspects. And the first is some analytical expressions, and it can be divided either by some analytical solutions to the one-dimensional Webster horn equation. For example, the left picture is a family of hyperbolic exponential horn proposed by Selman. And this one is a tractrix curve shaped tractrix horn, and it's just a special mathematical curve without too much rigorous validation. And another class of horn design is the heuristic or empirical design. And For example, here shows the conical exponential horn and the Mentari horn. These are designed using a method of trial and error, and usually with some parts of regular shape. And all of these shapes are usually not optimal. So in recent 20 years, there has been many attempts to optimize the horn shape using a numerical method. And pioneering work is this one by Bunsen to optimize the radiation efficiency of a 2D waveguide. And the optimized horn geometry can vary from simple 2D to fully 3D optimization. And the optimization goals cover the radiation efficiency to the directivity properties. But this method, most of them are based on FEM or BEM numerical model, and may have a disadvantage at high frequencies because it will need a large number of mesh grids, and the computational cost can be high. So I have developed a new method based on the multimodal method and localized geometrical parameterization to solve this problem. And first, let's see the problem is we consider a baffled 3D asymmetric horn with fixed throat. The throat is a narrow input end of the horn and fixed sized mouth at B. The mouth is a larger part, the output part of the horn. And what we want is if the horn is fed with a plane wave, and the part of the wave energy will be reflected and part radiates to the surrounding air. And we want to find optimal boundary shape to maximum the radiation efficiency and the desired far field distribution. The discrete model is shown here. And in the first step, we approximate the horn as a series of short connected short cylinders, as shown by the red line. There should be many segments to well approximate the continuous horn shape. And at each segment, we know that here is a uniform waveguide, so the pressure and the velocity on the axis of propagation can be represented as a series. It is an analytical solution, and this orthogonal bases are the exact satisfies the red boundary condition. And we can also define at every point in the discrete model the impedance matrix and the admittance matrix to connect the pressure and volume velocity model vectors. And to solve this problem, we start from the output end, the mouth. It's ended in infinite baffle, so we have a closed form solution for the radiation efficient matrix, and then we propagate the matrix from the mouth to the throat. And then at the throat, we give it excitation, a source, and then propagate the velocity or pressure modal vector back from the throat to the mouth to obtain the sound field and the velocity at the mouth. And finally, we can use the Hankel transform to get the far field directivity function. And we have noticed that there are two types of discontinuity. And here shows this. First is expansion and contraction. And here, the position where we consider the matrix or modal vectors are labeled as 0, 1, and 2. And in terms of the impedance or admittance matrix, we should propagate it from the position 2 to position 0. And these 4 different equations represent different cases. The expansion, the combination of the expansion and the contraction. For example, if an expansion followed with an expansion, we should use the first equation to propagate the impedance at position 2 to impedance to 0, because we allow the shape to vary everywhere along the axis. So we should consider all the cases. And give another example, if we have a contraction followed with an expansion, and in this case, we should use the last equation to propagate the impedance at 2 to the admittance at 0. And similarly, for the modal vectors, we should propagate it in an opposite direction from the throat to the mouth. So we usually express the modal vector at 2 in terms of that on 0. And again, for 4 different cases, we have 4 different expressions, and these expressions follows are derived followed method proposed by Rowe in a 1972 paper, and these are numerical stable, so that we will not encounter some stuck or numerical errors in the implementation. And the matrix appeared here. The F matrix or the V is the matrix describing the modal coupling at the discontinuity. And in the uniform part, these matrices D1, D2, D3, and ZC and YC are representing the modal propagation in the straight part. So in a summary, if we want to calculate the sound field using the multimodal method, we should first propagate the impedance matrix and then propagate the modal vector in an opposite function direction. And then at the throat, we can obtain the reflection matrix with in terms of the throat impedance matrix, and its left corner element is the plane wave reflection coefficient, here RP, and then we can find the closed form solution of the directivity function, as long as we have obtained the mouth volume velocity. And here gives an example of calculation result. For an exponential horn shown in the middle picture, we can calculate the reflection coefficient spectrum and the sound field inside of the horn, and finally the directivity pattern in the far field. And the white line here shows the 6 dB beam width or coverage angle of the horn. We can see a strong, evident beaming effect, which means the beam width decreases as the frequency increases. And how can we develop a multimodal optimization based on the model? A simple idea is to define a series of design variables directly as the radius of each segment. In a forward problem, a continuous shape is sampled to get these segments and the radius. And now we reversely to use this radius to as a design variable. And this kind of parameterization is localized parameterization, because if we change a variable, change one variable, and the discontinued model, the stepped model only change in this local segment, and the others will not be changed. So, but this model will induce a geometrical error, which means the exact model we obtained is the discrete one, cannot be a continuous shape. But in practical manufacture, we need a continuous one. So the continuous shape is manually created using, for example, interpolation. So there would be a geometrical error, but as long as we take a large number of variables to simulate the continuous shape, the error can be small. And next step, we should define different objective functions to satisfy our design goals. And we have considered 3 different cases. The first is the radiation efficiency optimization. The objective function is the mean square of the reflection coefficient at several target frequencies, Fi. And the second is a constant directivity optimization. If we want the directivity pattern at in over a wide frequency band become independent of frequency, we can define the objective function at each frequency is the standard deviation of the far field intensity level. And we can then take the mean value for the frequencies we considered, and finally get an expression like this. And the last case, we want to optimize the megaphone to optimize the on-axis directivity. And here I take an idea that a vibrating piston on an infinite baffle will have a high frequency beam effect, which means on-axis pressure would be very high, or the beam width will be very sharp at high frequencies. So if I can modify or adjust the horn shape to make the mouth, the pressure field at mouth to simulate a vibrating piston, or only allow the plane wave to come out. And we know that the plane wave can propagate to a long distance. So it's not rigorous, but and not published yet. It is a recent investigation. And but this the advantage is we can to maximize the piston or the plane wave mode at the mouth, and to suppress all the modes from higher than the second mode, higher than 2. So this is also expressed in a least squares form. So it is in a uniform least squares form, can adapt it to the following optimization schedule. And sometimes we want to we desire the horn shape to be regular, to be easy to manufacture, or even to avoid some avoid the algorithm to be stuck in the iteration. So we take 2 measures to avoid irregular shapes. The first one is Tikhonov regularization, is to add a term in objective function. And here x is the second order difference of the radii. And this fraction is constant in an optimization process. And the epsilon here is an adjustable coefficient that control shape regularity, and we can adjust it. The larger it is, the more regular the shape is. And another strategy is called filtering. Means that we can directly iterate with x instead of r. And this help to promote smooth shape update, and can make the optimization faster and more stable. And finally, we can summarize the minimization problem, because we want the searching space to be maximized. So we want to carry out an unconstrained optimization, and the nonlinear least squares problem can be solved in a gradient-based algorithm. It will always it does not guarantee a global minimum, but it's efficient to find a local minimum. And in this method, the gradient can be solved in a semi-analytical way. And we use an efficient and stable algorithm, the Liebenberg-Marquardt algorithm, to solve the problem. And once the optimization stops, we can verify by a criterion for local minimum. That is the infinite norm of the gradient has decreased several orders of magnitude. And here I give some results. The first case is the radiation efficiency optimization. And the simplest case is to optimize a single frequency. And the A and B shows the 2 cases, one for the low frequency region, K equals to 2. Here K has been normalized. So, and the second is the target frequency is 16 at a mid to high frequency range. And both in both cases, we can we obtain good results with a significantly decreased reflection coefficient compared to the initial shape. And in the optimization, we use 126 variables and 16 modes. Because it's not very dense, the resolution is not very high. So we need to check the result with the finer resolution to interpolate the optimized shape with 1000 segments and compute it with 128 modes to check the results. And we can see in the right column that after we increase the resolution, it still works, but the minimum value has raised to about -3, order of -3. And we can also see that for the low frequency optimization, in the frequency band out of interest, it can be raised compared to the initial shape. So we have to explore some wideband case. And this one shows a multiple frequency optimization. We have 3 target frequencies, and the similar result can be obtained. And again, we see that the performance checked with the finer resolution can be a little raised up, and in the band outside the target frequency, the spectrum is even higher than the initial case. But if we carry out a wideband optimization, covers 3 octaves for a real dimension of a horn from 2000 to 16,000 hertz. And the target frequencies are set logarithmically spaced in each octave. And we can obtain significantly discrete spectrum in the target frequency band. And if we verify this result, it is remain almost the same. So, and this horn is also validated through experiment, but the result isn't given here. And the second case is a constant directivity optimization. In this case, in order to avoid some wrong results, for example, the negative radius or the radius is 0 to with no radiation. In this case, numerically can also have a local minimum with optimized optimized directivity, but it's wrong. So in order to avoid this, like what has been done in the literature, we simultaneously optimize the efficiency. So the objective function has 3 terms. This term is to control the constant directivity, and here we assign a coefficient here to adjust the relative weights, and the last one is a regularization term. And here gives the results, and the second is the reflection coefficient spectrum comparison, and The third one is optimized directivity pattern. And the red lines shows the frequency band we want to optimize. And we can see the reflection coefficient spectrum and the directivity pattern have been optimized simultaneously compared to the initial exponential horn. And in this table gives the average value of the reflection and the standard deviation of the directivity index and the standard deviation of the beam width. We can see the decrease from the exponential horn. And the last case is the optimization with respect to the on-axis SPL. And it's also a wideband optimization. We start from conical horn to optimize the on-axis directivity to have the results shown by the blue line. And I compared the results with the other classical, typical horn shapes. They are conical, parabolic, and exponential. And we can see the on-axis DI. The optimized horn has the largest DI throughout the target frequency band. And here shows the the sound field inside the optimized horn and the exponential horn. We can see that the wavefront in the optimized one at the mouth is nearly plane with a node circle, but for the exponential it's circular. And we have noticed that there are some fluctuations or ripples in the shape. And a question is, if we smooth out these ripples, what would if the DI spectrum be influenced? And we conduct it, you can see the zoom of the small feature of the original optimized shape and the smoothed out shape. And we can find it's counterintuitive that at high frequencies, the on-axis DI of the smooth shape is a little bit lower than the fluctuated one. So we may think about the small ripples may contribute to high frequency directivity. But in the low frequency, the influence disappeared. And here gives the sound field inside this smooth and original shape. And we can see the smooth one indeed have a smooth, more smooth wave field, but the on-axis DI is decreased. So here is a summary. This method has advantage of it is a efficient gradient-based optimization approach, and it allows for good shape flexibility. As you can see, it can find some shape with small ripples, small features to obtain good results, but it also has some limitations. First is geometrical error because the optimized result is a stepped discontinuous shape. So we can image that this error in some cases may have strong influence. And the second is accurate optimization requires a large number of modes. And in this case, the computational cost can be high, and the computation time is long. And the third is we only consider the infinite baffle as the radiation condition. And we are now developed some improved model to solve these problems. And the second part in this talk, I want to discuss subwoofer design, the bandpass subwoofer design. Here is the introduction. The bandpass subwoofer system is a type of low frequency loudspeaker system. And the key feature of it is the driver is does not radiate directly to the surrounding air, but is mounted on an inner baffle inside the enclosure. And the box only radiates through these ports. And the enclosure can be regarded as a system of Helmholtz resonator. And its pressure response is of a bandpass shape. So it's called the bandpass loudspeaker. And it can be categorized by different forms of configuration and implementation, which means we can have a different number of cavities and tubes and resonances. And we can use auxiliary electrical circuits to aid its response. And the order of the bandpass subwoofer is the sum of its low frequency and high frequency attenuation orders. And it has been widely used in some applications such as the home audio. It can be used as a low frequency effect channel for the surrounding air of a surrounding sound system, or it can be used in professional audio because the power is relatively high. And here the pictures shows several different types. The left is a fourth order, and this is second is a sixth order, and the third one is a triple chamber eighth order. And these three enclosures are products of both companies. And the last one is made by me 3 years ago. It's also a it's also a sixth order enclosure. And you can see in these two pictures, the driver is the inside of the enclosure. And first, I want to introduce eighth order bandpass, which called the active eighth order bandpass subwoofer. And why we call it active eighth order? Because it composes a sixth order enclosure, and the enclosure is assisted with an active second order low pass filter in front of the power amplifier. So the overall response is a simple multiplication of the second order low pass filter response with by the sixth order bandpass response. And its shape is the response shape is symmetrically bandpass shape. And the sixth order enclosure has the following two different configurations. Both of them have two cavities, a front chamber and a rear chamber. But you can see the difference is in type 1, the two ports contribute to radiation simultaneously, but for the type 2, the front and rear chambers are connected through a port, and only one port contribute to radiation. So the 8th order bandpass have two types in terms of the enclosure configuration. And how to design it, a simplest way is the response alignment. Early used by Tiller and Small. And the principle is to align the system response to a desired bandpass shape response. And as long as we get the desired response, we can align the rational form response to it to get the right system parameter. So the first step is the desired response. We can get this using a frequency transformation or a reactance transformation from a low-pass prototype. The low-pass prototype is given in this form with three unknown coefficients in the denominator. And here shows several typical response, which may be, you may be familiar with this. The Butterworth, blue line is the Butterworth response, and the red line is the equal ripple Chebyshev response, and the yellow line is the quasi-Butterworth third order response. And the transformation change the frequency variable to a reactance function. And if I substitute it to the prototype, we can get an 8th order polynomial in the denominator. But if we direct align this denominator to the frequency response function of the 8th order system, it can be, of course, it can be solved numerically, but it's not efficient to analyze. So we take another method to direct transform the pose of the prototype, low frequency prototype to the low frequency prototype has a pair of two pairs of conjugated poles, and after transformation we can get 4 pairs of conjugated poles of the bandpass response as shown here. And after we get these poles, we can assign each pair of shows or poles to the low pass filter, and the other 3 pair of poles combined to and assigned to the 6th order enclosure. So we have 4 different ways to make the factorization or separation of the response shown here and labeled class 1 to 4. And in the alignment, the low pass filter, we can make the desired response and the response of the active filter or digital filter, make them equal. And for the 6th order enclosure, we only need to solve the 6th order equations in to align their denominators. And then we can solve the system parameters, including in Taylor small form, the driver resonance frequencies and total quality factor, and the resonance frequency of the defined Helmholtz resonance frequency of the cavity tube. And the compliance factor is the ratio of the acoustic compliance of the driver to the box volume. And for the first enclosure, we can solve it with the analogous acoustical circuit, and to derive the polynomial coefficient in terms of the system parameters. And then after alignment, we can get this driver parameters. And for the second type enclosure, we can do in a similar way. And finally, we can obtain the analytical expressions for all the system parameters. Here, the table gives a total of 8 different design system groups, including 2 types and 4 classes. And then we can calculate some system performance we are interested in. And the first performance parameter is the AMID. It is defined as the system response attenuation relative to the desired response. We remember that when we align the 2 responses, they can differ by a constant factor, AMID. It's important because this factor is specific for bandpass subwoofer. For direct closed box or vented box system, AMID is always equals to 1. But for bandpass subwoofer, it can be take any value larger than 1 or smaller than 1. And it's also the attenuation factor of system sensitivity relative to the loudspeaker driver sensitivity. The driver sensitivity is the case for the driver mounted in an infinite baffle. So it's then we can do some parametric study to learn how this the dependence on the system type and the response ripple factor and the bandwidth factor. And the second system parameter is the reference efficiency. It is defined as the ratio of the output power to the input power at the center frequency. And here, this relation expresses the nature of the trade-off between the system performance, which is proposed by Taylor and Small. Is the efficiency is proportional to the third order of the cutoff frequency and proportional to the total volume box volume. And here is a constant called the efficiency constant, and it is a figure of merit that describes the beneficial you can get from specific type of enclosure. It's regardless of the low frequency cutoff or the volume. So it's very important. And for the its order bandpass enclosure, we have this expression for the constant. And again, we can do some parametric study. And we can also find out the displacement response and the transient response of the bandpass subwoofer. And in the displacement response, the subwoofer has two minimum, and near the minimum, the displacement of the driver is very small, and the nonlinear distortion can be suppressed. And here gives some conclusions of the parametric study. The most important one is for overall alignment, that means the overall desired response, the bandpass response. If the relative beam width is larger than 0.82, it's not very wide. So the range can be very practical. And in this range, the system type 1 with the alignment class 4, it's labeled as alignment group 4. Use the highest AMID, and a high AMID is desired because it's attenuation, it's a relative attenuation or between the system and the driver. So we want this value to be high. And another important conclusion is both types of active systems require the same driver and active filter design, which means the same driver can be used to realize either type of system. And if you use the same driver to realize these two types of systems, they have the same maximum efficiency constant and overall displacement function. And next, I will introduce another type of 8th order system, the triple chamber 8th order bandpass system. In 1992, Schreiber published enclosed patent describing several multiple chamber bandpass subwoofer, and there are, as I counted, there are a total of 7 different types of triple chamber, triple tube bandpass systems, and they are all of them have symmetric 8th order bandpass orders. And here only give a typical one with 3 chambers and only 1 port to radiate. And it can be regarded as a structure, a combination of structure of a part blocked by the red line is previous mentioned 6th order enclosure type and simple Helmholtz resonator, and it contributes to a 2nd order low pass. And the combination would give symmetric bandpass attenuation order. And again, we can analyze the response using analogous circuit. We can calculate the volume velocity flow out the tube MP3, the mass reactance MP3, and to obtain the response. And here gives the response. The denominator coefficients are given here in terms of our defined system parameters. And it looks very complicated, but it still have analytical solutions not given here. It's quite long, and the system response can be aligned to the desired symmetric response given here. In this case, we don't need to factorize the denominator, just to solve the eighth order equation set. And again, we can get the mid-band attenuation factor. It's important. And here I give 2 examples. The first is Butterworth shape, and the second is equal ripple response. And the dashed line gives the desired response, and this solid line gives the system response. And you can see their difference is characterized by AMID. And they have, and these 2 design, I have made the cutoff frequencies to be equal. And we can see in the Chebyshev response, the AMID can be much higher than the Butterworth response. But in terms of the transient or the displacement, it's maybe it may have more ripples than the Butterworth response. But if we want high sensitivity or sound louder, we can choose a response with small ripples, which can be hard to be sensitive. And again, we can solve the displacement function. And in this case, because the enclosure has 3 chambers, 3 resonances, it has 3 displacement minimum. So the average distortion in the passband can be even lower. So in general, why the bandpass loudspeaker are popular in audiophile. It's because it's powerful, and it has a low nonlinear distortion, and so it sounds very clear with enough output and maximum output. So in summary, in terms of the active 8th order bandpass, there are 8 types of configurations, and one of them, the class 2 with type 1, has the highest AMID and relatively high efficiency constant. And there are in total of 7 different types of triple chamber subwoofers. They have not been studied one by one, but each of them can be studied with the same method, and we can finally compare the response to choose which one is better. So that's all of my talk today. Thank you for listening.